Hey class, it's Mr. Hofstad here with Unit 5, Lesson 7, all about the force of friction. Got some new concepts here, 3 examples. As always, let me know if you have any questions at all about this material. Send me an email, send me a comment, and I'll try to clear it up for you. So, we should all have some idea what friction is, but our nice fancy physics definition of it is that friction is any force that resists the sliding of one surface over another. So just like normal force, it has to do with surfaces, and those surfaces need to be in contact. But here, it's instead of being perpendicular to the surface, it will always act parallel to the surface. And the force of friction will always resist motion. So V, again, is our speed or the direction of our motion, and our force of friction will always oppose that. There's no such thing as a friction force that adds energy or adds some force to a system. All right, here's our calculation. It's also on our formula sheet. No need to memorize it. We will be working with it a lot though. So our force of friction, denoted by big F and then subscript lowercase f. So that'll always be force of friction. Like all other forces, we're measuring it in newtons. And we have just a quick definition of it. It's how hard the surfaces are pressed together, right? Fn will always be a reactive force between two surfaces. And the harder something is pushed against the surface, the more friction it's going to be, right? If I have my calculator here and I'm sliding it, right, there's not much friction. But as soon as I start adding extra force down on it, now it's really hard to move it, right? And that's because I'm adding this normal force down on it, increasing how hard the surfaces are pressed together. All right, next we have this new symbol. It is called mu. I'm going to spell that wrong. But shout out to all the Mewtwo fans. This is your symbol. It looks like a little lowercase u with a tail on it, right? That's how I like to draw them. It's a u with kind of the tail of a y. And that we will always use in physics, at least for physics 20, to symbolize our coefficient of friction. So what that means in layman's or real person term is that it's how rough the two surfaces are. So a higher coefficient of friction would mean the surfaces are rougher, right? So there's going to be more friction. And you can just see from this equation that if you increase our coefficient of friction, our mu, we're going to increase our force of friction, which makes sense. If mu is really small, like paper rubbing against this whiteboard, right, versus something really rough, like sandpaper, right, that's going to have a higher force of friction. It's going to be harder to push it along, right? More resistive force to that motion. All right, let's try an example just working with this one first equation, the magnitude. So here we have a 37 kilogram object. I'll draw it out. And we have a normal force, and we have the force of gravity. It's being pulled east by 400 newtons. Sorry, it's also 37 kilograms. Being pulled east at 400 newtons. So the motion is going this way, right? You don't necessarily need to draw in that part, but we know that there's this force of 400 newtons pulling it across the level surface. We know the friction, the coefficient of friction, which is our mu, so I'll write that down, is equal to 0.68. Recognizing that coefficient of friction doesn't have any units. It's like a modifier. We're not changing our units. Force of friction and normal force are both measured in newtons, So we don't want to change the units with this force of friction. It's just changing how much force of friction we're experiencing. It wants us to determine the acceleration of this object. Okay, so we know there's this force applied to it to the right. We also know that there's going to be this force resisting it, our force of friction. So in order to find the force of friction, we need our normal force. So we're going to break this up into a vertical and a horizontal section. In order to solve this horizontal component, force of friction, we first need to find our normal force. Then our second step can be to solve for the force of friction. All right, so in our vertical direction, we have a mass. We know, or we assume, I guess, that we're on Earth, and we're going to use Newton's first law because we're not accelerating up or down in the vertical direction. So that's our principle of physics 0, Newton's first law. I'm going to start referring to principle of physics and Newton's laws. We do need to get used to this principle of physics terminology. It's on the diploma in Physics 30 and on some of our exams, and it's just an important part of the Alberta curriculum. So our principle of physics 0, Newton's first law, states that our F net must be 0 in the vertical direction, and from that we can determine that the normal force has to be equal to the gravitational force, which is going to be equal to our mass times acceleration due to gravity, which is 37 kilograms times 9.81 meters per second squared, giving us a normal force and a force of gravity of 362 and some change, 362.97 newtons. Right, so force of gravity would be down, normal force would be up. We have this value. We're done our first step determining normal force. Now we're going to break it down to our horizontal. In our horizontal direction, we don't have balanced forces. We have 400 newtons here and some other value here. Right, because it's actually moving, we know, right, that it's being pulled east, right? It has some acceleration. We'll assume that that acceleration isn't 0 for now, unless this force of friction was actually equal to 400, which is not very likely. You might come across it once in a while, right? We're going to be using our principle of physics 2, Newton's second law. And with Newton's second law, we know that our net force is equal to our mass of our object times its acceleration. In order to find the net force, we need to have our applied force of 400, and we're going to take away our force of friction. Right? Capital F, lowercase force of friction. And that will be equal to our mass times our acceleration. That's what we're looking for. All right, now I'm going to substitute in my values and the formula for force of friction. So just carrying this over here, we have 400 newtons minus, and then our force of friction is equal to coefficient of friction, 0.68, times our normal force, 362.97 newtons. And that all is equal to our mass of 37 kilograms. I'm just substituting all the values I know from this equation in here, times our unknown acceleration. All right, so we're going to multiply those together, right, and divide both sides by 37. So 400 minus the product of those, all in brackets, divided by 37, will give us an acceleration, which is equal to 153.2. That's from those two guys. divided by 37. So that would be newtons over kilogram. And if we break up newtons into its standard or fundamental units, we know we have kilogram meters per second squared divided by kilograms. We have the correct units, and we get 4.1 meters per second squared. That'll be positive, and with our reference system, which I didn't write, north, east, south, west, we'll call it, where north and east are positive, this is going, it would be more correct actually to call this up and down because we're working with our vertical components. Anyways, we know we're going east 400 newtons, right? And we ended with a positive number. Since I left east as positive, positive answer means we're going to the east. That is our final answer for this first question. All right, next little section of the notes, we're talking about different types of friction, and this can be a little confusing, but it is important. So let's get through this. We have two types of friction. One is kinetic and one is static. So kinetic, just like kinematics, is all about things moving, whereas static, which might be a new force for us, is things that are not moving. So kinetic will always refer to things that are moving. Static will refer to things that are not moving. And that is actually related to static friction. It's about charges that are no longer moving. They're stuck in place. But that comes up in physics 30. So for now, kinetic friction, static friction, where kinetic friction occurs when the object is moving. It'll be a constant value, and we're going to denote it with this little subscript K for kinetic. So our force of friction, kinetic, right, with our little k, relies upon our coefficient of friction, and that's our kinetic coefficient. So we're going to have different values for coefficient of friction depending on whether the object is moving or it's stationary. Right? Stationary starts with an S, static starts with an S. There's a good way for you to keep it straight as well. All right, so kinetic friction, we use coefficient of kinetic friction. Makes sense. We're still using the same general formula. But static friction, we're going to have a different coefficient of friction. So a question will need to give you two different values. If it's starting at rest and then starts to move, you need two different mu's, or two different coefficients of friction, right? Mu k, mu s. So static friction is all happening before the object starts moving. There's still some force applied to it. It will resist the intended motion. So this is the motion it takes to get something moving, right? So as I try to push my calculator, there is resistance until I get it moving, right? There's kind of that idea of a threshold again, or a required force applied to it to begin that motion. It's not going to start moving on its own, and it will resist that motion with this static friction, right? So it resists the intended motion, the direction you were trying to push it. It's a reaction force, right? Just like Newton's third law, equal and opposite reactions. And it increases as the applied force increases. All right, what that means is as I push harder and harder, this static friction will be resisting more and more and more until it finally starts to move. So the static friction isn't constant. It's not a fixed value like kinetic. It'll increase, right, as more force is applied to it, up until the point where it can no longer resist the intended motion. Then it'll start to move, and we will have this new now kinetic friction. All right, so eventually it reaches that maximum value. It can no longer resist that motion. It'll kind of have that resistive force overcome, and it'll start to move. So the force of static friction is less than or equal to the coefficient of static friction times the normal force, right? Up until the point where we have our maximum friction force static, right? So we will have an increasing force of static friction up until our maximum point where it begins to move, and this is what the graph of that looks like. So here I'm not pushing at all, right? We'll think about the calculator in my finger. I'm not pushing at all, and then I start to add pressure, and as I keep pushing harder and harder, I'm climbing up this graph. Notice that the calculator still isn't moving, and I'm applying more and more force. So the force that I'm applying is still being matched by this friction force until eventually I reach this threshold, this maximum static friction. Now my calculator starts moving, right? So there's this peak, and as it starts moving, something very interesting happens. Now the kinetic friction is constant, right? It's a fixed amount, but it's lower than that maximum static friction, right? So you can almost think about it. This isn't very accurate, but it's a good approximation and a way for you to remember it. Like our calculator and the surface it's sitting on has some invisible little bonds or some magic glue resisting it. And as it starts to move, we've broken those bonds, and now it's able to move more freely than it did at that maximum. All right, so pretty interesting physical property. That's true for any two objects, any two surfaces. So, sorry, it's usually, but for our course, we'll just say always. So for any two surfaces, the coefficient of kinetic friction is usually smaller than static friction because we have this hump, this threshold that we have to overcome. And once it's moving, right, there's less magnitude of friction. Our kinetic friction will be smaller than our maximum static friction. All right, this is an important graph. Make sure you're familiar with all the axes, right? So the force of friction is increasing as we're increasing our applied force until we get to our maximum static force, and then it's going to drop down, and it doesn't matter what applied force we have now, we'll have a constant friction force with our kinetic friction, right? So be familiar with these axes, right? Our y-axis and our x-axis, and the two sections where we have our static friction or our stationary object and the moving object or our kinetic friction. All right, let's try our second example. I do believe we have 3 examples today. Yes. So we have a 70 kilogram oak desk on a level oak floor. So we have the same surface, but we have 2 different coefficients because we have it starting at rest. So we need to use our static friction. So that's stationary or static. And this is when it's moving. And you can see our static is bigger than our moving, or our kinetic. We want to determine the friction force if the applied force is first 200 newtons and then 450 newtons, right? So the way the question's presented, some of you might have guessed that this would be our stationary situation, and then our larger force will have overcome our static friction, right? We'll have come over this hump and then back down to our kinetic friction. Okay, so that's just what I kind of see when I start doing this, but you can do it with the math too, and it'll make sense that way. So we want to determine our maximum static friction. Force of friction, static, maximum. is always going to be equal to our coefficient of static friction times our normal force, where our normal force here is going to be same as force of gravity, which will be 70 times gravity. 70 kilograms from our table, and our gravity, 9.81, which gives us 686 newtons. Right? So both of those are 686.7 newtons. We can find the maximum force of friction, right, which will be this peak up here, right, from this equation. So our coefficient of static friction, because it's not moving yet, times our normal force. So we have 0.5 times our 686, which will give us 340, sorry, that's a 7, should be a 4, 43.35 newtons. Okay, so anything less than 343, we're going to still be on our stationary part of the curve, right? So for part A, since 200 newtons applied is less than our static max force of friction, we have our object is remaining at rest. It's not moving yet. It's still climbing up that part of the graph. Right? So for any question of this type, we know that if we're under our maximum static force of friction, we're now working with this idea that it's not moving, so we're working with Newton's first law. Newton's first law, principle of physics 0. Newton's first law. So if F net is 0, then our force applied needs to be equal to the force of friction. Right? So here, our force of friction, static because we're not moving, because we're under our threshold or that maximum static friction value. So the force of static friction is equal to the applied force of 200 newtons. Right? We're pushing it with 200 newtons. It's not moving. Since it's not moving, we know there's no acceleration. Net force is 0. Applied force is force of friction. Right? That's our first situation. Now for our second situation, we have our applied force greater than our maximum static friction. So since F applied, the force that we're pushing it with, 450 newtons. Since the force applied is greater than our static max, so now we're moving. Our desk is moving. So we have a greater applied force than that max static friction force. Our desk is moving. And we are working with our kinetic friction. So with kinetic friction, it'll be constant as long as it keeps moving. So therefore, force of friction is equal to our force of kinetic friction, which is equal to our coefficient of kinetic friction, mu k, times our normal force. So we now have 0.3 times our 686 we calculated in the first part. So the force of friction kinetic is equal to 206 newtons when we throw in our proper significant digits. All right, so it really depends whether we're working with kinetic or static. If it's moving, right, we've overcome our kinetic friction hump and we have a constant force of friction. But before we get to that amount, we're now working with our static. All right, I will get back to this last example in a little bit.